Okay, welcome everyone.
Okay.
Let me check the recording's going. Yep. So welcome to week 2 of Steel's Yap, and today we're doing compression essentially. First thing we're going to talk about is buckling. So buckling is going to matter for compression design and flexural design. Compression design, keep in mind, is week 2 and 3, and so your first assignment will be tension and compression design. Buckling will also be relevant for flexural design, which I believe is your second assignment. So that's week 4 and 5. So buckling is a very important concept. Actually, hang tight. Oh, let's just go over quickly what we're going to talk about today. We're going to go over the types of buckling and how buckling will relate to something called the slenderness ratio, which, if you've done concrete, we don't touch on. No mind. But yeah, compression design. There's 2 parts to it: the section capacity and member capacity. The TLDR for this is section capacity is to do with your section, cross section, how strong it is. So essentially, that's what we did in week 1, right? Tension. We had 2 versions of calculating how strong the section was based on different failure criteria in week 1, right? Week 2, there's one method for calculating section capacity. However, it covers 2 failure modes. I'll explain that later. And then next is a member capacity, and this is largely to do with buckling failure. So this is where buckling is gonna play into it, but it's the whole idea that if you have your I-beam drawn out in 3D, right, it's to do with how it's gonna fail along its length, right? So if something buckles, it's gonna fail along your longitudinal axis, as opposed to the section, right? And then yeah, and then just basically getting this factor, alpha C, is going to require a lot of steps, a lot of like folders within folders and stuff like that. Yeah, any questions so far? That's the gist of it. Okay, cool. So first we'll talk about buckling. Oh great, this isn't loaded. Hello? We're back. Okay, so buckling. This is like from solid mechanics essentially, right? It might have been like one of those topics at the very end of solid mechanics, which you might have skipped over because there's other shit that was in your exam and this isn't really accessible, right? But the idea is that essentially, if you have axial loads, right, compression. Actually, if you have compression, this doesn't really work in tension. Then your member, here's my demonstration. I'm going to do this. My pen. One sec. Okay. Here's my wooden piece. And so we have a major axis, right? So along this depth is a lot stronger than the minor axis, which is really flat, right? So if I push against this, which way is it going to buckle?
The minor axis.
Exactly. It's gonna
Oh.
it's gonna buckle along this axis, right? Because it's a lot weaker, right? And keep in mind, buckling is a elastic form of failure, which means that the material can return to its original form. So it's not plastic failure like yielding and stuff, right? So this is technically a buckling failure. It just hasn't failed yet. It's gonna propagate failure if you continue loading it. And it's going to fail a lot faster than if it didn't buckle. So imagine this thing somehow didn't buckle. You put in all the axial strength, it's actually going to be pretty strong because it's not going to be in flexural tension, right? Yeah. Anyway.
I have a question.
Yeah.
Which one's the major and minor axis?
It depends on your shape. So for this shape and for an I-beam, right, you're going to have a very distinct major axis because I might just draw it out in the...
Did you do it inertia?
Sorry?
Did you do it inertia?
Yeah, exactly. That's exactly right. So it's whichever inertia is stronger.
Oh, okay, yeah.
Yeah, moment inertia, yeah. But usually have you guys started looking at like one steel and stuff?
Yes.
Have you noticed that, say this is a UB, universal beam, they look like that, right? And then columns look like this. Yeah? So what's different?
longer on the web.
Pretty much. And usually the flanges are less wide. So why do you reckon that is for beams and column?
Because the universal beam is supposed to take on shear, and columns not really much so.
More bending, yeah, shear a little bit, but like pretty much.
Because on the universal beam, you're applying a load from the top.
Yep.
Right? So
Yep.
when you apply a load from the top, in this case our major axis would be like the vertical one,
Yes.
right? So
Yes.
it would be stronger in that way.
Usually it's like this. You call XX axis the major axis.
Yes, that's right.
Yeah, and then this one's the minor axis, right?
Oh,
So- So bending, like the way that I showed you, where it was like kind of buckling,
yeah.
that's really really weak for beams, right? But what kind of loads are you expecting beams to take?
Dead load, like.
Pretty much gravity.
Oh.
That's it. Like you rarely expect beams to take much in terms of wind because that's not what they're designed to do. So on like the exterior of a building, right? So if you have building like frame and shit like that, the big rafter like frame, all that, those are beams. Kind of the ones that are on the edge but will receive a decent amount of wind load are actually going to be usually box sections, hollow sections, because those actually are a little bit better in both directions.
Oh.
But these big ones, they're usually I-beams.
Got it.
But can't wind come from like any direction?
But it's shielded, so there's gonna be like glass and facades and shit out here. But so the beams are protected from the wind essentially.
Oh.
Yeah,
So
because they're supporting the majority of the building, but they don't really take the sideways loading, right?
Got it.
But universal columns, right? Actually, just a quick question, right? So we've established that IX is greater than IY for the universal beam, right? What about for the column?
They're the same.
Are they?
Fair.
It's all the way
universal.
around.
For you,
Other
it's
way
column.
around? Are you sure?
Yeah.
Universal column. IY should be greater,
IY should be greater.
isn't
You sure, bro?
They're equal.
They're not equal there.
Oh.
They're only equal for a rectangular hollow section.
Oh.
Oh, a square hollow section.
it? IX. So IY means it's bending like
Sideways.
sideways. Facts.
So which one's stronger for the column?
A very good up-down
Still
direction.
Still up down, right? But is it by the same degree?
No.
So for an I-beam, IX is usually 10 times bigger than IY. Something in that ballpark. But for these, they're more closely together. I don't know, 3 times bigger. Something like that. Do you see? Like, so when you orientate these columns vertically, right? And then they're taking on your axial loads, and yeah, essentially you have to check buckling in both directions. Because the, bending can basically happen in both those directions, essentially, right?
Yep.
Make sense? Because then it's not a matter of gravity load. Like gravity loads are just acting, basically like this. I don't know why I'm redrawing it. Gravity loads are just acting like that, but then they can buckle x direction, y direction. But there's always a stronger axis, unless it's a square hollow section, which sometimes is the
What about
case.
circular hollow section?
That works as well, but circular hollow sections are not really. I haven't really, because circular hollow sections are hard to connect things to.
What about a triangular one?
So, like,
It's
try,
it's
like-
strong.
Bolting it is like it can only be bolted like that and stuff, right?
What if it's a square with a circular hollow section?
Wait, what?
Hey, yo.
like circle inside.
Yeah.
I've never seen that my whole life. Okay. But yeah, makes sense. Any questions? Okay. Yeah, buckling is really important, basically. Some fucking formula. This is like Euler's formula or something for buckling. But essentially, the idea is that buckling is to do with the end conditions. So that means how your column, let's say, is connected to, say like a floor below and a floor above your building. Wait, no, not your building, above your column, right? And so it can be pinned, it can be rigid, or it can be somewhere in between. Make sense? Do you remember we were talking about in the crash. Actually, no, I'll get that later. But yeah, just pin that and keep it in mind. Here's something which I showed in concrete. If you guys have seen the concrete yaps before. Now these numbers 12. Keep in mind, this is not from the standards. It's not from the concrete standards. And sorry, can someone turn on the aircon? It's kind of hot. Celine, if you could, please. Just click the power button and turn. Yeah. Thank you. So these numbers are pulled out of thin air because the formula for slenderness ratio isn't actually length to width or whatever. It's effective length to radius of gyration. That's like the actual determination of your slenderness. But this gives you some idea because for me, I like to be able to fucking visualize what a short column and slender column is. And when you're talking about radius of gyration, it's a number that's really hard to fucking visualize, basically. And so I just have a number, 12. So basically, if your length is about 12 times bigger than your width, this is in the most generic possible case, which is like for a solid square shape, then that's considered something like a short or a stubby column, right? Whereas if it's greater than 12, roughly, that's where it's slender, right? Make sense? Okay. We'll talk about radius of gyration later, but it's something that you've probably seen in solid mechanics before. It's the square root of I over the area. So that's so you can actually have two versions. We'll talk about it more in depth later. But Rx, Ry, right? Because it depends on that axes. You're talking about the major axis, minor axis, all that stuff. And all you do is you change whether it's Ix or Iy you're talking about. Make sense? But the area is, like the cross-sectional area is not directional. So that will always stay the same. Yeah. Any questions?
No, sir.
Okay. So, I'll just quickly show you this diagram to give you an idea of what causes buckling and how it kind of works on it. Yeah. So, you have your normal yield stress. So, we've talked about yield stress in terms of tension, right, last week. You know how it's like yield on the gross section? Similar effect happens in compression. But when something happens, when your column or whatever's being compressed, when that yields, that means it's actually reached its full material strength. That's actually a good thing. So it reaches like a plastic failure mode. However, if the member is too slender, it essentially causes like an early failure due to buckling. Right, so it's an elastic failure. So essentially, imagine I had this wooden whatever column, and it was more stubby. So it was like as thick in both directions, right? And I pressed down on it. It would actually be pretty strong in compression. You could probably use that as like a table leg or something like that, right? However, since it's so thin in this direction, it's not going to utilize the entire material, essentially, in the direction that is stronger, because it's going to fail in the direction that's weaker first. That's what's happening with buckling, essentially, right? Why are you pointing like? Does it make sense? Or? Okay, cool. So, essentially, yeah, I have a realistic curve, which is the blue line here, but the black line represents what the buckling failure mode, essentially, right? When your material has reached the buckling stress, which is the yielder's stress. Yeah, and then like you have your yield stress, which is constant based on material. Anyway, am I just yapping too much? Just tell me to shut up if it's too much, because this isn't even in the course. It's just context. Yeah.
Wait, could you please reiterate why if one side is weaker than another, it will just fail in that direction before the other direction?
Yeah. So.
Like, what happens if it's like square?
Oh yeah. Okay. So wait. Let me give you two examples, right? These are two cross sections.
Yeah, I was like, holy shit. It's practically making sense that I lost.
So pretend these have the same cross sectional area, right?
Wait, also when you say cross section, do you mean that it's like this way or this way?
Yeah.
So cross section is you have a beam or something, And all we've done is we've cut anywhere
Well,
across
how
it.
do I know if it's a beam or a column that I'm...
Oh, it doesn't matter. So if it's a column, the cross section is cutting across it.
Okay.
Usually we assume everything in our design is like prismatic. So prismatic means it's the same shape across the entire length. So it doesn't matter where you cut it. So it's like a rectangular prism, I guess. Yeah. Anyway, so imagine you have two cross sections, right? They have the same area. If I just applied axial compression, which one's going to fail first? Same amount of axial compression.
The long one.
Hey,
Yeah, why?
it's more slender.
Exactly. It's going to fail in buckling in the minor axis this way first, right? So it's the same cross-section area. We're spending the same amount of money to produce it. We've
Okay,
just
okay.
done it in efficient shape.
But what about for the top one? When will it buckle? Because they're the same, like...
Oh, yeah. So depending on... it actually depends on the length. Like that way. Do you know what I mean?
Oh, okay.
So if this is stubby, if its slenderness ratio, whatever, is stubby enough so it doesn't buckle before it reaches material failure, it's just gonna crush.
Okay.
So it's like a crushing failure that doesn't have any. Yeah. So that's like a yield failure for steel. Because like, I don't know if you're thinking about wood or steel right now, but for steel it would yield and crush. Right. But if it's too long, like that, it's gonna buckle as well. But it's random which direction, because both directions are as strong as each other. Right?
Okay.
Makes sense though? That's the general concept. Yeah. Any more questions before we move on?
What do they use with the number? Like
Oh.
the geometric slenderness ratio.
Oh, so they'll come later.
Oh, that's what come back.
Yeah, I haven't even talked about the
Oh,
formulas
okay.
actually yet. Like the formula you saw earlier
Yeah.
is like a theoretical, like Euler's. Yeah, it's not in like the standards.
Oh, we don't actually use it.
Nah.
It's just
If you wrote it down, cross it out. It's gonna confuse you. Anyway, so here's like actual compression design. So it's quite it's similar but different to tension, because tension you're doing two simultaneous checks, right? But in compression and for flexure, this will be the case as well. You always have to do the section check first and then the member check. Yeah.
Nothing.
Okay. So this thing on the left, we're kind of familiar with this notation now. It means the axial, N means axial, right? Compressive force that's factored. Factoring being the star. So this is assuming that we've already applied our 1.35 G, 1.2 G plus 1.5 Q, and whatever other wind cases or something you have in mind, right?
0.9 W plus 1.2 G.
Yeah, all that. Make sense? Okay. 0.9, oh sorry, the capacity reduction factor is also 0.9 in compression. No dramas there, because tension was 0.9 as well. Compression is 0.9. Flexion is going to be 0.9. Basically, that number comes from the consistency of the material in that action. So it's probability based. And steel is incredibly consistent. So we only reduce the capacity that we think it can withstand by 10%. Concrete, what kind of numbers were we saying? Do you remember?
0.85.
0.85 all the way down to for brittle failure mode.
0.6.
0.65 for flexure, right?
0.65.
And then 0.75 for shear and stuff like that. Concrete's just, I mean, steel's just 0.9. So it's much more consistent, right? If you do timber, it's a net after you apply all the reduction factors is like 0.5, 0.6. It's pretty low. Yeah. Anyway, so the first failure mode that we're going to look at, sorry, we're checking the section failure capacity, and essentially we're going to look at two failure modes. The first one's yielding, so that's what I talked about. That's like if, okay, essentially, it's where you get your whole crushing thing, right? And there's no buckling at all. That's that's like an ideal situation, I guess. Oh well, it's not ideal because if you design every section like this, you're gonna be wasting a lot of money, essentially. Anyway, now local buckling. This is slightly different to what we've been talking about because we've only been talking about buckling in terms of the entire length of the member. But if you recall from the crash course, right, we talked about individual parts of the section being able to buckle as well, right? So that's what we can see. Sorry. It's gonna take a sec to load. you see on the left here? That's like if a flange element or something buckles. So that depends on how thin this is versus how long it is, essentially, that flange element coming off of that I-beam or column section. Okay, so here's a formula. So if you're going to write down anything, this is it. NS represents your section capacity, right? And then KF is your form factor, AN is your net section, and FY is your yield strength, right? So we've kind of seen two of these before, right? This and this, right? Is it coming up?
Yeah.
Yeah.
So what's the difference between A net and A gross? Anyone?
A net is like the area of the cross section
Yep.
minus the holes.
Yep.
And gross is including the holes.
Yes, pretty much, as in like filled up, so no holes, right?
No holes.
Is A net along the failure plane?
Yes. So if you have your bolts, so if you have like a section like this, and your bolts are like here or something, I don't know. That's the area you subtract, right? So it's a rectangle, not a circle. Yeah. Yeah. Okay, what's FY?
Yield strength.
Yeah, pretty much. There's nothing more to it, really. It's just whatever you get from table 2.1. And you check the grade of your steel. So this is like grade 300 steel, 350, whatever. Look at the table.
Oh, I had a question real quick.
Yeah.
If they tell us to use, or if they say like 350 grade steel, so something like that. So in our initial calculation we use 350.
Yep.
Then we check the area or whatever. But then if they give us a different value for FY, so like 360.
Oh yeah. Oh sorry. So yeah. So in initial sizing, use it's called like the nominal stress grade or whatever. So like if it's like if it's grade 350, in your initial size, just do that, because it depends on it's a function of the thickness of your plate, right?
Yeah.
So let's say you're building up your section, or even on one steel, they'll like pre-bake it. If this is like 6 mil, or if it was 9 mil, actually no, let's do the threshold number. There's a different value for yield strength based on 8 mil or 9 mil.
Okay.
So one is like 360, one's like 340. These I'm butchering it. Don't copy this down. But like, do you know what I mean?
Yeah.
So like that's why we just do the nominal stress for the initial guess. Once you get more information, you replace it, right?
Yeah.
The other thing to note is that for compression design, usually they don't really care so much about the bolts unless it specifically says in the question. Tension design, bolt design is like really important, because you have like whole fast fracture like propagated by cracks and stuff, so like the bolt area. For compression design, they don't really bring it up again in the course. So like the workshop questions, they might not bring it up. So it'll just say like pretend that AG is A net. You know what I mean? This is getting pretty laggy, so I'm gonna reconnect to it. Okay, sorry, we're back. Okay, now I want to talk about form factor real quick, right? So this goes. Have you guys done questions yet for this course?
No.
Okay. Are you familiar with the idea that like there's custom sections versus like standard sections? Or, so basically, if you have a standard section, it's going to be on one steel, basically. That's if you have your like universal beams, universal columns, welded beams, welded columns, rectangular hollow section, all that crap, right? If you have a custom section, and this is usually assignment material, sometimes like long workshop questions, things are a bit harder. Tension checks are about the same for whether you have a custom section or a standard section, but for section capacity for compression, it's really fucking AIDS, right? And the whole reason why it's AIDS is because you have to manually calculate KF. So in one steel, KF is fucking given to you. KF can be 1 or less than 1. So if it's 1, what do you reckon like the kind of meaning is? Yep. So-
One means it's symmetrical.
No,
The centroid is in the middle.
that's KT,
Oh.
I think.
Okay,
KT, that's for fast fracture. I think it's KT. Here we have a different one. This is the form factor.
is it to do with the end supports
Oh, so we're just talking about the section right now.
section? Okay. Oh, the section.
Yeah. So once you're talking about it in terms of the entire member, that's like you're thinking of the next step.
Yeah.
The member section failure. Yeah.
It's like when you got the edge pieces and then
I don't know where you're going with this.
it's the edge pieces where they're not holding the load.
Okay.
Oh, wait, you were at the no
Isn't that what it is?
fourth. Oh yeah. I see what you're talking about. Okay, we'll get on to that. But basically this number, like it's a TLDR. This number can be 1 or it can be less than 1. So 1 means it has full strength, right? What does that tell you about local buckling?
The whole section's gonna buckle.
If it's 1,
It's not gonna buckle.
it's not going to buckle.
Oh.
None of the section buckles if it's 1 because it has its full strength.
Yeah.
So if it's less than 1, what does that mean?
Some of the section could buckle, or all of it.
It's like the
Probably
dilatation.
not all of it, but yeah.
Closer to 0, the more.
Yeah, more of it's buckled, right? So how do we determine that? Let me show you on this next page once it fucking loads. Fuck. So blurry. Fucking hell. Oh, we're good. Okay. It's the effective area over the gross area. So we know what gross area is. Let's find out what effective area is. Effective area is much more aids to calculate essentially. So here we have an I-beam, but we're going to custom size it for whatever reason, right? So what's the best way to split up this section to check for local compression buckling, do you guys reckon?
3 rectangles.
How would you describe those? You can say like flange, web.
Yep. 2 flanges on a web. 1
They're
flange,
not the whole
2 webs.
So like that, and that? You reckon?
Yeah.
2
Seems
flanges
like
and
the
a web.
most intuitive way.
So that would be the most intuitive way if you're calculating whatever section properties, say like BD cubed on 12, like, you know, all that shit for moment of inertia, right? Because that's what you've always done.
Mm-hmm.
But here, there's areas that don't buckle. Correct?
The middle.
The edges buckle, but
Yeah, exactly, that's
What's
right.
connected to the web.
So you pretend these parts are unbuckleable, right? There's actually there's a short reason and a long reason. The short reason is like pretend it's kind of got rigidity from multiple sides, and so it can't buckle, right? And so for a rectangular hollow section, it would be the corners because you have multiple kind of flat plates connected to it. But the long explanation is to do with residual stresses in terms of how the steel is formed, and so essentially you have less compressive stresses in these areas as the steel like cools down, and it's just it's something to do with residual stresses basically. Whatever, who cares? The easiest way to interpret it is when multiple edges touch. Those are like the unbuckleable areas, right? Okay. And so conversely, we have areas which are more prone to buckling, right? Which I've drawn in purple there. Once it fucking loads. There. Anyway, just yeah, maybe you can see that kind of. But like the purple areas, we have the tips of the flange and we have the middle of the web. So it's just the furthest parts away from your unbuckleable areas, essentially, right? Anyway, so here's how I would split up this element. I just put 1s for the flanges, like the flange edges specifically, and then 2 for the web. The thing is, these have to be different elements. This has to be a third element if this is an unequal I-beam. So if your bottom flange was like a bit shorter or something, these would have to be separately calculated, right? Yeah, makes sense?
yes.
Okay. So here I've just yeah. You can see how the numbers kind of work out if this fucking loads properly. Hope my internet's fucking installed by next week properly, because this is annoying. Okay. So we have like width and thickness. So the width, sorry, in this case, is always going to be the dimension that's bigger. whereas thickness is like how thin your plate is or whatever, right? And so for every single element, right, so 1 and 2, we do the top formula there, highlighted in blue, that's for flat plates. The bottom formula there, highlighted in blue, is for if you have a hollow section. Sorry, a circular section, I should say. So it's to do with your outer diameter. Usually circular sections would be circular hollow sections. And so, yeah. Make sense? Okay, cool. Now the thing is about your web element and the flange element is they're going to behave a little bit differently. Would you expect, assuming it's like a UC or something, right? So given that this is roughly representative of the dimensions of our section, right? Would you expect the tip of the flange to buckle more easily or the middle of the web?
For a column.
Yeah, let's just say a UC.
Tip of flange.
Yeah, why does that make sense in your head?
Because it's like an edge piece.
Wait, what was the case?
Sorry?
What was the loading case?
It's axial, so it's going into it, right? Compression through the middle and through the whole thing. Yeah.
Because the force goes on the centroid and then spreads out.
Let's just say there's a bunch of mini arrows that go across the entire thing and it's like evenly distributed.
Would it be because they're receiving the least amount of support?
Yes, pretty much. Yeah.
'Cause the web is supported by 2.
It's kind of like a cantilever, right?
Yeah.
It's like a cantilever beam. Think of it like that, right?
If
Whereas the other ones are being supported from two sides. However, that kind of changes depending on the proportionality. So this is like a beam, right?
Yeah.
Do you see how this one might actually be more susceptible to buckle in the middle of the web?
Yeah.
It really depends on.
It's
That's why you have to do a
further
check. But yeah, that's why in the table that you can see here, there's longitudinal edges supported, one and both, and so you'll have different values depending on whether you're talking about the flange or the web, the middle of the web, right? That's pretty much it. And just keep in mind we're doing hot rolls most of the time, unless it's specified. Sometimes it's heavily welded as well. Usually custom sections I think are heavily welded actually. And I think one steel, when it comes out of one steel, it's hot rolled. I'll tell you why.
Is it because one still produces hot roll?
Yeah, it's actually called 3rd edition hot rolled structural steel products. So it's all hot rolled, right? Yeah. I might show you guys this at the end, but it's really useful. It's in the Sigma lectures thing, right? Okay, so we need to calculate the effective width. So there's formulas for it, but let's just understand it intuitively. I think this drawing helps a lot. Your effective width is basically the width of your elements that you calculated that don't buckle. That's it. So if we're looking at the web element here, so BE2, the effective width is equal to the width. So what does that say?
All of it is becoming used in carrying force.
Yeah, without buckling, right, in the failure mode. Yeah. Whereas if the effective width is less than, what does that mean? Oh, yeah, effective width, sorry. Yeah. Is less than the width of your flange.
The edge pieces will crumble away.
Yeah. So if BE is less than B, 1, for element 1.
And it's redundant. Both parts
Not.
redundant, but
Yeah, it's just that's the amount that will
they're
be
not
ineffective.
as strong as like what it would be if it was the effective width.
Yeah.
At least part of it will buckle.
And so, essentially, your end goal, right, is to find the form factor. Oh, sorry, it's down here. Your end goal is to find the form factor, right, which comes from AE. AE is literally all the blue shit. It's your effective area.
Uh-huh.
And then KF, if it's 1, it means your effective area is exactly equal to your gross area, right? So KF is 1. But if it's less than 1, it means parts of it are red, essentially, right?
But how do you decide BE?
Oh, that's in this formula above. So you have to do it for every single You have to calculate for every single element, the ones and the like. Here, there's two types of elements, right? One was representing the flange, two was representing the web, right? What happened for the web is we actually got a BE value bigger than B. So what does that mean?
It means that it's actually like fully effective.
Yeah. So you set it back down to B because like geometrically it can't be bigger than B, right?
Yeah.
So that's why there's this bit here which says less than B. Yeah, see that part? Yeah. But if it's less than B, it means that it was just calculated as, you know, like there's some ineffective area basically. Any questions? Yeah.
When you said, can you please scroll up to like when you said the K factor equals 1?
Yeah.
I think I missed it, but basically you said if it equals to less than 1, it's more likely to buckle, right? Like the more of the area will buckle.
Yeah.
So if it equals to 1, does that mean it will never buckle?
Section wise, yeah.
Like this way?
You talking about a column?
I don't know. Like,
It won't do this type of buckling.
Oh,
Yeah. It won't do this type of buckling. So that's a section. That section in particular right there, buckled.
Oh, but instead it would do
It-
the top, the one above.
That, or you have to check for member buckling. So Euler buckling is the entire
Oh, yeah,
this
the
wooden
entire
thing. That's Euler buckling.
Oh, okay. So it just
Yeah.
means that not a specific part will be
Yes.
there. Okay.
Yeah. So it's more along the entire longitudinal axis that it could buckle. That's Euler, which is what we're checking for member capacity.
Can it be both types of buckling? Like
Yeah. So actually that brings me on perfectly to the next type, right? Let's hear member failure capacity. Once this fucking loads. Alright. So do you look at this one now? The member capacity NC is a function of NS.
Oh.
So if NS was already reduced because of your ineffective area, it's going to have a flow-on effect. Do you know what I mean? Yeah. It's going to have a flow-on effect to your... So it can buckle locally, and then it causes the Euler buckling to be exaggerated. Yeah.
So it's you always have to have local buckling first.
You always check for local first.
But
This one's not a matter of like preference. So for tension design, you can check fast fracture or you can check yielding first. It's up to you. This one you have to do in this order because one's dependent on the other.
So it will always local buckle before.
Not necessarily, but it's just how we do the calculations because one will exaggerate the other. So it could be completely fine in section, but then it can Euler buckle. So one doesn't have to happen without the other.
Okay.
But remember, so the section buckling, the section capacity determines how strong your entire member is. Yeah.
So when it comes to section failure, how do we know if it? Let me quickly scroll up. How do we know if it's gonna crush or if it's gonna like fail at that local spot?
Doesn't really matter. So it covers both. The formula covers both.
Oh, okay.
So but basically it's implying if KF is 1, that failure mode is only going to be the yield failure, assuming it doesn't fail the member check.
Yeah.
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 I think it'll make more sense once I show you the table of like this PDF
Yeah.
at the very end.
Okay, sure.
Yeah, in terms of how they all play into each other.
No worries.
No worries, cuz.
Wait, I think Farhan, this, just to make sure, you know this graph?
Yes.
The formula covers both lines, is what you're saying.
Let's go back to just to show the YouTube audience.
So usually you'd have to check for the black line and also check for the red line
Yes.
and check which one's min.
So
But
yeah,
You said your formula covers both at the same time.
this Australian standards covers both.
Without
Yeah.
that formula, yeah.
So the red line is analogous to if KF wasn't a thing.
Compression failure, right?
It's as if you're saying your section capacity is equal to only Fy and An.
Yeah.
That's no buckling.
Mm-hmm.
That's the red line.
Mm-hmm.
This one is accounting for KF and it's accounting for our next step as well, which is along the other line, the Euler line, the alpha C. Actually, wait, KF is confusing, to be honest. Sorry. Let's pretend KF is 1, so it doesn't buckle along the section.
Mm-hmm.
This black line is more accounting for Euler failure. So Euler failure is just talking about member, global buckling.
Oh, but then if you have local little bit bending, then it will like bend
Yeah.
even more exponentially.
It might exaggerate this line or something down, like, you know what I mean? That's if you have KF is less than 1. But the black line, that formula is just for Euler buckling, which is what I'm going to talk about
Right,
next.
but you just said we don't need to check for yield failure.
What?
Didn't you just tell Farhan?
No, I think.
No. So yield failure here.
Uh-oh.
Yield failure is included in this formula. Yield failure is as if KF is 1.
Yield failure is if it doesn't buckle but it just crumbles.
Yeah.
And it's in that first formula.
Yeah, but because once you do KF, right? If KF is 1, you've already checked for yield failure, essentially.
Yeah.
And if KF is less than 1, you've checked for yield failure and local section buckling.
Oh, so basically.
Yeah, it's included.
KF
It's all
equals 1
included
is
in the
always
formula.
going to be bigger than your buckling.
Yes. It means it doesn't buckle.
Okay.
So that's the failure, assuming nothing buckles. Yeah.
Henry, do you have a USB-C charger by any chance?
Yeah, I've actually even got one right. Oh, when I was Ken's. What?
Then
The
what
Wi-Fi
about the critical buckling?
You can use Ken's one if. Oh no.
I have a charger.
Wait. What?
I have my charger.
May I use it?
My laptop charger.
Is this mine? I can't tell.
It is yours. Can I
Oh, this is
open
mine.
it?
Yeah, it is yours.
Oh,
I
okay.
I scrapped it.
You can rack it if you want. Okay. Sorry. Where were we?
Yeah, I like it.
Do you guys need a break or anything? Or just power through? Power through. Let's fucking do it. Okay. Sorry. Let's talk about member failure
This one here.
more formally. Once it fucking loads. Okay, so we push along its longitudinal axis, and if that longitudinal axis length L is big enough, we experience Euler buckling, or global buckling, or member buckling. There's 3 words for it. Yeah.
Can you please repeat that sentence?
Okay, so if you have a long enough member, it starts to become more and more prone to Euler buckling, or global buckling, or member buckling. There's 3 words for it, right? Yeah. Okay, so this is a deceptively simple looking formula, but how to calculate alpha C is like kind of annoying. There's multiple steps to it. Okay, but it's essentially a slenderness reduction factor. And you know how we talked about how Euler buckling is a function of slenderness ratio? Yeah, we'll unpack that. So, the first out of the 2 main things you have to calculate here is the compression member constant, right? So that's alpha B. So you need alpha B to calculate alpha C.
You need alpha A to calculate alpha B.
In the derivation in the slides, but you don't need it when you're doing questions.
Is there an alpha D that you
No.
need?
Alpha A, if you see in the slides, fucking ignore it. It's troll. Because it's already summarized in like everything you need for alpha. Oh, sorry. It's alpha A I think is something to do with this part of it.
Period.
Yeah. So don't worry about it. Yeah, do you have a question?
What if you're a sigma?
Okay. Oh, but let's quickly talk about this, right? We have 2 tables. One is if KF is 1, and one is if KF is less than 1. What did we say that meant?
That's it.
Buckles, not buckles.
Locally or globally?
Locally.
Exactly. So even the global part, like,
Is affected.
yeah, is affected by that KF factor from the local part, yeah.
Is that why the graph is affected? Is that why there's 2 lines on the graph? Is that
No.
Is that why the universal compression is affected by the local compression?
There's too many theoretical questions going on. I don't know how to answer these like
okay,
super
that's
well.
okay.
But yeah, sorry. We'll go back to that at the end or something because there's too many thoughts going on. Okay, so modified member slenderness, lambda n, right? So this is basically everything we've been talking about in terms of slenderness ratio, but compacted into one formula, right? So one is to do with, again, KF, so that's to do with your section and its proneness to buckling. The other thing is material strength is going to affect your slenderness as well, so that's Fy. Okay, let's talk about the other two things here. One is effective length and one is radius of gyration, okay? So Farhan, you know how you mentioned earlier the gamma method stuff?
Yeah.
In my little note here, it says gamma methods for 2D or 3D frames. That's going to be one of the focuses next week. So next week I'll do gamma method on top of 2 examples. That'll be next week.
Lovely.
But right now we're going to do the idealized end restraints method. So that's just talking about if your end restraints on your column are pinned or rigid or a combination of them, right? And the other thing is radius of gyration. So we'll just talk about that a little bit more, but you guys kind of get that one already. Okay. So when you do your modified member slenderness, right? We have the slenderness in the x direction and the y direction. Why did we say this was important? So going back to this wooden thing.
Because if it's more slender in one side, then that's what you're measuring.
Exactly. So, and you said more slender, right? Because
So
something being more slender
It'll
means
be
it's
more
more prone to buckling, right?
buckling.
So that's why we do the max.
Yeah.
Because we find the one that's more slender, like the direction that's more slender, right? Okay.
Yes, Mr. Sigma.
Yes. Okay. Here's where it gets a bit trippy. Well, there's 2 parts. The first one's not too trippy, and the second part's a bit more trippy.
Oh wait.
Yeah.
Before you go on, with the x direction, y direction, is
Yeah.
it just intuitive which one's going to be the worst case? Or you actually have to calculate and see which one's the worst case?
So again, it's based on Ix, Iy, right?
Yeah, but like you can just look at the shape and see it's obviously.
Usually you
You
can.
can just tell.
I think what
You
he's
usually
asking,
can.
how many steps can I skip?
Yeah.
Yeah.
You can
but
usually
you can
tell.
just skip it, right? It's intuitive.
It's
but-
intuitive, yeah, I would say it's intuitive, and yeah,
And it's based on dimensions of like the column.
Yeah,
Is it like, do you
Yeah.
have to calculate IX and IY?
isn't it given in one steel?
it's given in one seal unless you have a custom section. So actually, let me skip ahead to that real quick. So it's radius of gyration. Do you see this note on the right? Custom shapes. Calculate Ix, Iy area to find Rx, Ry.
Oh man.
So that's that whole thing where we were talking about how you can break this up. That's that. Well, if these are even, you can make this a 1. But then you need to do your shift, parallel axis theorem shift. Okay, let's go back for a bit. Yeah. So effective length. Sorry. Let me zoom in a little to this diagram. So I use this to explain it in the crash course, but I'm gonna say it again for you guys to drill it in, and also just the people who haven't seen this basically explained, right? First thing is brace member and sway member. So let's say we're talking about columns in a building, right? So basically, if you have a frame like this, what's gonna happen if I push it a little bit with wind or something like that? It's gonna fall right over, right? Because it doesn't have any lateral restraints, so nothing's restraining it in that horizontal direction. So this frame is probably fine vertically, right? Because all the loads will transfer down into the ground. But it's when you go laterally, this thing's gonna sway. This is a sway frame. Okay. What happens if we do this? What's gonna happen if I put a force laterally to it?
It's going to.
Sway.
Oh wait, it's not going to move.
This one's not going to sway.
It's not gonna yeah, exactly. And the way that structural engineers like to think about this is load transfer into the ground. If the force goes into the ground, it doesn't sway. Okay. So I'll give you an example. This is a good example.
If it does go into the ground, doesn't it sway? As in
Oh, sorry. The forces. If the force can transfer into this joint and then go down here into the ground,
it's not swayed.
yeah, because the ground disperses the stresses. Right.
Oh. Makes sense.
Yeah. Actually, to be honest, I think this is technically fine as well, because in terms of trusses and stuff, it'll go like this and then into the ground as well.
It actually makes sense.
So I was about to say something wrong there for a second, but I think that's right. Okay.
I think you do have to check X and Y.
You do?
Just reading ahead.
Okay.
You get to it.
Oh, but you intuitively You do it intuitively.
What if
Yeah.
there's a member in the middle, a brace in the middle, that changes your LE?
Exactly. I'll talk about that in a second.
But
Okay.
it's still intuitive.
Yeah, you do it based on intuition, I would say. Okay, anyway, so that's what brace and sway means, right? So you have these different numbers for KE, your effective length factor, based on the end conditions now. Now, I know the fucking internet is like really pixelated there, but you can kind of make out that very left picture has rigid connections. This one has like pinned and then a rigid, and this one has 2 pins, right? This is for the brace member. We're basically checking how big the C shape is, right? That's a C shape, that's a C shape, that's a C shape, right? Relative to your member.
Yes.
So how much of the C shape does the left picture take up roughly?
Small C.
70%. 70%. Okay, the second one?
86%.
85.
It's like 8.
And then this one?
1%.
1%. You bang on. Okay, now what about these sway members?
They go off the
Big fucking C, right?
Huge.
Huge fucking C. So that one which says 1.2 is 1.2 times the member length, which I didn't draw very well there. So it's exaggerating how long your member is. And what did we say about longer members in terms of the proneness to buckling? They're more prone, right? So when you have a sway member, essentially you're exaggerating how badly your building's going to buckle.
Yes, man.
Okay, any questions?
No, sir.
Okay, so onto what Lockie was mentioning. LEX, LEY. Now, if we have this wooden thing again, right? Our LEX and our LEY. See the camera. See. Our LEX and our LEY are going to be the same as the length. Let's just say that's, I don't know, 50 centimeters, half a meter, right? However, if we can restrain it like this, right, in the middle, I'm not doing this very well. Okay, if I'm holding my hand like this, right, it's still fine to like it's still going to be just as likely to buckle in the minor axis, agree? Because my hand is not actually stopping it from moving in that way, right? However, if I try to push it along its major axis, my hand is actually stopping it. So it's not shown very well because the major axis doesn't buckle very much for this thing, right? But if I do it this way, right? So my hand, I'm going left and right with my hand, right? And oh, that's the major axis. That's fine. But now if I push down, do you see what's happening with the shape?
It's 2 buckles.
Yeah. I'm restraining it. Yeah, exactly. It's 2 C's. I'm not sure if the camera can see it very well, but it's like an S basically. It becomes an S. So my hand is restricting it from buckling in the minor axis because it can't really go towards me. Make sense?
Yes.
So that is what you have to think about in terms of LEX and LEY. I'm drawing it here. So say you have that beam and you have your XX bending along, you know, the major axis and your YY along the minor axis. It's braced in the Y direction here. Because think about how this is going to deform if it's bent sideways. That's kind of what I was doing. Right?
Like along the X direction, right?
So in the XX direction, in the normal way you expect a beam to bend, having someone grab that, pretend that bracing is my hand, having someone grab that isn't really going to stop it from bending downwards, right? It's only going to stop it from going in towards the arm.
Yes.
Yeah? So, yeah, that only really starts to matter when you look into frame systems and things like that. Yeah. It's fine for a lot of the simple questions, right? Radius of gyration, we talked about that a little bit. It's basically just a matter of finding your IX, IY, and dividing by A to find, yeah. Okay. We're nearly done, guys. It's alright. So, this is the way I would recommend. So there is a table for alpha C. I wouldn't recommend using it. It's a really, really long table in the standards. And it's summarized by this graph. So you might as well just use the graph. So alpha B is the thing that depends on whether your thing was like KF is 1, KF is less than 1, or if it was like hot rolled or heavily welded or shit like that, right? That just changes which line we're looking at, essentially, right? So you go up and down depending on what alpha B was. The important thing is the slenderness ratio, modified slenderness ratio, which is along the bottom axis, right? So you come from the bottom axis, say it's like 100, you go up to whatever line you were looking at, so say it's 0, you bounce left, and there you go. That's your alpha C value. So remember, alpha C is a modifier for. Remember, it's
For the sectional
exactly.
sectional load.
It's alpha C and S. So what is having an alpha C of 0.55 say
It says that your compressive strength is 0.55
of your section strength, right?
of your section strength.
Which means how much has buckling essentially, Euler buckling essentially, fucked up your capacity?
By 0.45%.
Yeah, yeah, pretty much. Yeah.
Is the graph on one AS41?
No. So this is from a designer's handbook. It's on the slides. So that's why I've included it in my notes, but you can only find it on the slides, that book, or my notes. So you can't find it in the standards. The standards only includes a table, but the table's fucking AIDS. See what I mean? So this is a really, really useful graph.
Does Brian expect us to use a table rather than this?
No, use this.
Mashallah.
Because it can only, it can only fuck up by so much.
It
Yeah.
looks like fluids.
Yeah. It's gonna be like the second half of geotech is all these fucking graphs, bro.
Fucking hell. Fucking hell.
Oh no.
Okay, yeah, anyway, yeah, that's the end of mine. Yeah. Any questions? Okay, let's just have a look at the effects of buckling quickly. So we go to this. We go to members subject to axial compression. Oh my god. Download it.
Wait, so local buckling,
Mm-hmm.
for the case where like it fails across the whole section,
Mm-hmm.
that's not considered global? Or is global just like when the whole beam bends?
Yeah. Yeah, that's it.
I see. I see.
Ahmed,
Ahmed.
he does a screencast, but I fucking love him.
Yeah, he does, eh?
There's a what?
He does like
Screencast, pre-recorded things.
He's
Oh,
so,
let's go.
he's so sexy.
I'm still recording, bro.
Hi, Ahmed. Wait, isn't there universal beams right there?
Needs to be for members subject to axial compression.
Oh.
Here we go. There you fucking go, bro. No. Member capacities. Here we go. Okay. So
Oh my God.
let's continue that thought process. So this is already factored. Do you see how it says phi? Phi is 0.9. And then NS. So that means your
Sectional
section
load
capacity. Exactly. So that's treating LE is equal to 0. So we don't care about how fucking buckling length is, right? That's like the max it can take, right? And then as your member gets longer and longer, it gets reduced. That's NC.
So to find it in between those, so like if you were to find like let's say 20, right?
Mm-hmm.
Then how would you find?
Oh yeah, you can interpolate it, the numbers.
Uh-huh.
But this is you don't actually do this in this course. This is what you do in like industry, because
Oh.
you don't do hand calcs in industry.
So
You just
if he
fucking
gives
look at
us
this
a
table.
question, then he'll give us something that's definitely on the table.
This table, or are you talking about one steel?
Oh wait, he won't.
He went.
It's
This
the
is
same.
this is from work. This isn't from the
It's
course.
not what-
This is more like for your understanding, and it's
Oh,
also
oh.
for double checking your assignment
Okay.
that you're getting like roughly in the ballpark at the right numbers.
Okay.
Yeah, because if you're getting like this times 100, is wrong.
Okay.
Yeah, makes sense. And it even says like grade 300 and whatever.
Period.
Period. So this is buckling about x-axis. There's similar ones for y-axis. There's similar ones for not welded beams, but universal beams, universal columns. Fucking yeah.
Yes, ma'am.
So just look at the chapters part of that. But anyway, I'm gonna stop.